Okay, in this presentation we are going to look at the analysis of a piecewise probability density function. This is part of the random variables series of videos. So this is our problem. The probability density function PDF, which is denoted f of x of a random variable x, is given as follows. So it is a casewise or a piecewise probability density function. There's three components to it. So the probability density function is 0.2 for x between -1 and 0. And between 0 and 1, it is 0.2 plus cx, okay, where c is a constant term, and 0 otherwise. Okay, so between -1 and 0, it has one form, 0.2, and between 0 and 1, it has another form, 0.2 plus cx. So the first question is, find the value of cx, and then what we're going to do is work through the rest of the question there. Question B is find capital F of x, that's the cumulative distribution function. Then we're going to find the probability that x is between 0 and 0.5, and then we're going to find the expected value of x. So this is our function again. So essentially what we're going to do here is integrate this and let that equal to 1. So just notice that we have a range of values there, 1 to 0, and 0 to 1, and so essentially minus 1 to 0 and 0 to 1. So essentially what we have there is two components. So essentially what should happen here is that the definite integral of those two components should add up to 1. So we're going to calculate them separately and add them up and see what the value is that will give us a value of 1, a total area under the curve of 1. Okay, so that's it. That's the game plan here. To find the value of c, we need to ensure that the total probability is equal to 1. I sort of touched that point there anyway, but that is actually the general formula that we would use. The integral from -infinity to infinity of f of x dx should equal to 1. Because the values are only relevant, the probability density function is only active between -1 and 1, we will sort of adjust those limits accordingly, because everything else outside of that limit evaluates to 0. So given the piecewise function, we need to split the integral into two parts, okay? And essentially the evaluation of those two integrals should add up to 1. Okay. So let's do the first part there, the integral of 0.2 dx, and we're going to evaluate that between -1 and 0. Well, 0.2 dx is, when we integrate that, it is 0.2x. And when we evaluate that between 0 and -1, we get x is equal to 0, that's the upper bound, we get 0.2 times 0. And when we evaluate the lower bound, we get 0.2 times -1. And the difference of those two is 0 minus 0.2, which is 0.2. So that one's actually straightforward enough, but just to sort of confirm the case. So for the second part, the integral of 0.2 plus cx dx, and we're going to evaluate that between 0 and 1. Okay. Again, we can split it up into two parts here, just to sort of make life very simple for ourselves. And we can evaluate the first component there just more or less in the same form that we have done in the negative part of the range of values. It works out to be 0.2. So we have the integral of cx there, and we're going to integrate that between 0 and 1. So the integral of cx is cx squared divided by 2. And evaluated between 0 and 1, that is just looking at x squared over 2 there. We have evaluate that at 1, we get 1/2. When we evaluate it at 0, we get 0. So the second component there of that integral evaluates to c times 1 over 2. C over 2 essentially. The total integral for the positive part evaluates to 0.2 plus c times 1/2. Okay. Now, including the negative part, which was also 0.2, the total evaluation is 0.2 plus 0.2 plus c over 2, and that is equal to 1. So 0.4 plus c over 2 is equal to 1. Working it out, we will get c is equal to 1.2. So that is the first answer there. C is equal to 1.2. So we're going to move on to the cumulative distribution function, and the approach is the same. So the cumulative distribution function, CDF, is denoted f of x, and that is obtained by integrating the probability density function. Just as a remark, what we are going to do is evaluate the two terms separately. So the first part is the negative part, where x is between -1 and 0. The probability density function in that part was 0.2, and we're going to evaluate that between -1 and x. Just as a remark, we use a dummy variable essentially. So rather than express the probability density function in terms of x, we will express it in terms of another variable, in this case t, and evaluate it to the upper limit of x. So essentially what we do is we get a term that is an expression in x, which is what we want. So that's the purpose of the dummy variable, just a placeholder while we are doing the calculations. So this one's straightforward enough. The integral of 0.2 dt between -1 and x, okay? So that is, again, that would be 0.2 times t evaluated between x and -1. So we would end up with 0.2 times x minus 0.2, which is plus 0.2. Essentially, the minus signs cancel out there. I hope I got that point across. So that's the first part of the cumulative distribution function, 0.2x plus 0.2. Now, we're going to do the second component here, where x is in the positive region between 0 and 1. Okay. Now, just as a remark, you would include the first term that we've done previously because it will be relevant. It is an integral from -1 to x. So essentially, we're going to break this up into two components here. So we have the first term, the 0.2, the negative region, and that must be included in this calculation. But we have the answer there. It's the first term. It evaluates the 0.2. So essentially what we have to do is evaluate between 0 and x, and we have to evaluate the probability density function in the positive region. That is 0.2 plus 1.2 times t, okay? So when we evaluate that between 0 and x, that will give us the probability density function of that would be the cumulative distribution function component for the positive region. Again, component, it's not the full expression. We do have to include the negative component there, as that will give us the proper cumulative distribution function. So anyway, 0.2 times 1.2 t. So when we integrate that, we get 0.2 t plus 0.6 t squared. And we're going to evaluate that between x and 0. In this case, we just put in x instead of t. And we get 0.2x plus 0.6x squared. Now also recall that we have to include the first term there, the negative region, as part of our cumulative distribution function, so that is 0.2. So overall, we get a cumulative distribution function of 0.2 plus 0.2x plus 0.6x squared. Now this is the important bit. How do we piece this all together? Okay, now this is actually the proper answer here. So essentially we break it up, we express it as a piecewise function or a casewise function. So we have 0 for x is less than or equal to -1. And then we have the negative region there, -1 less than x less than or equal to 0. And that will give us 0.2x plus 0.2. Then we have the positive region, 0.2 plus 0.2x plus 0.6x squared. And then we have 1 for x greater than 1. Okay. So it's very important to actually express the answer fully like this. This is where you get all the marks, essentially, this answer here. You show your workings, but this specifically is what you're asked for. And in the case of a casewise or piecewise probability density function question, this is what you're expected to deliver. So moving on to the next part, we are going to look at this interval probability. Find the probability that x is between 0 and 0.5. We're going to use the result from exercise B, which is a cumulative distribution function, okay? And what we're going to do there is evaluate the cumulative distribution function at 0.5 and 0, okay? So the cumulative distribution function of 0.5, that is in the x, this is in the third case here. Just go back here a second. where x is between 0 and minus 1, or sorry, 0 and 1. So we would use the third case there, 0.2 plus 0.2 times x plus 0.6 times x squared. Okay, so that is 0.2 plus 0.2 times 0.5 plus 0.6 times 0.5 squared. Okay, so that is 0.2 plus 0.1 plus 0.15, which is 0.45. So the second thing we're going to do is calculate the cumulative distribution function at 0. Okay, so we can evaluate it there at the second case, 0.2 times x plus 0.2, which will give us 0.2. Now, but just in case people have a slightly different setup for the integrals there, the less than or equal to, you can actually use the third case as well. That would also evaluate to 0.2. Just as a remark there, on the right hand side for x less than or equal to 1, the importance of less than or equal to and less than, it's just try and keep it sort of consistent internally, that you don't have too much duplication there. But ultimately, it doesn't cause too much problems if you do it slightly different ways. So anyway, f of 0, the cumulative distribution function, is 0.2. So our interval probability, the probability of x being between 0 and 0.5, is equal to 0.45 minus 0.2, which is equal to 0.25. Okay. And finally, what we're going to do here is calculate the expected value of x, the expectation. Again, what we're going to do is split this into two integrals. And so the expected value of x is the integral of x times f of x, which is, again, when we split it into two, we have the negative component there, which is x times 0.2 dx, evaluated between minus 1 and 0. And then the positive component, x times 0.2 plus 1.2 times x, evaluated between 0 and 1. So let's break that up into two parts there. The negative part first. So we have x times 0.2, which is 0.2 x squared over 2. Evaluated between 0 and minus 1, we get a value of 0.2 times, the upper value is 0. The upper limit is 0. The lower limit is 1. Minus 1. And when we evaluate that, we get a half. So 0 minus a half. Multiply that by 0.2 and we get our component equals minus 0.1. So let's look at the positive component here. The integral of x times 0.2 plus 1.2 times x. Okay, we can also split this up into two terms. So we have the integral of 0.2 times x plus the integral of 1.2 times x squared. And we're evaluating both of those between 0 and 1. Now, for the first term there, the 0.2 times x squared divided by 2, it's actually the same integral as the negative side, just different limits. So we end up with a value of plus 0.1. 0.2 times 1/2. And for the second term there, we have 1.2 times x cubed over 3, which is 1.2 times 1/3, which is 0.4. So for the positive region, the integral evaluates to 0.5. And what we will do now is add them both together to get our expected value, which is minus 0.1 plus 0.5, and that is equal to 0.4. And that is it. That's us done.